Hi, I'm Zhijun. In this video, I present our work, Self-Supervised Scene Flow Estimation for the Automotive radar. The input is two consecutive point clouds for 3D scene flow estimation. The output is a set of flow vectors which describes the displacement of points from cloud 1 to cloud 2. Scene flow estimated from point clouds have many applications, such as motion segmentation and dynamic 3D reconstruction. It can also be used to benefit 3D multi-object tracking, which is still to be exploited by researchers in the future. Current works in this area can be categorized into three types. Compared to image-based methods, these works can directly deal with 3D point cloud data. However, the methods focus on dense point clouds and cannot be readily applied on data of higher sparsity, for example, 40mm wave radar point clouds. As an emergent sensor, 40mm wave radar has many advantages over LiDAR. It provides radio velocity measurements, it is robust to adverse weather and different lighting conditions, and is lightweight and low cost. For scene flow estimation of 4D radar point clouds, the first challenge is the sparse nature of radar. Moreover, radar point clouds are much noisier and have lower resolutions. To make things worse, there are no public 4D radar dataset, and the costly radar scene flow annotation. The overall architecture of our method is composed of two modules. The ROFE module takes 2 point clouds as input and output a coarse scene flow. And the SFR module refines the flow vectors of all static points with a predicted rigid transformation. The ROFE module consists of 3 components. We use a multi-scale encoder to group local global features for each point cloud. Then the feature correlator aggregates costs between 2 frames. We concatenate features from different faces and form a flow embedding, which is fed into the flow decoder to derive a coarse scene flow. One important property of 4D radars is the radial relative velocity (RRV) measurements. Assuming the RRV of points keeps constant during the time interval between 2 scans, we can reach the equation on the right. The equation is used twice for static mass generation and loss function formulation respectively. To refine the basic scene flow from our RFE module, we first generate a static mass to classify moving or static points. We then use CAPTCHA algorithm to estimate the rigid transformation, from which we can obtain the rigid scene flow. Finally, we refine the flow vectors of identified static points with the rigid scene flow. We design 3 task-specific loss functions for robust self-supervised learning. The radial displacement loss measures the radial projection error of the predictions. Compared to traditional chamfer loss, our sub-chamfer loss discards outliers and tolerates small errors when computing loss values. A spatial smoothness is enforced by minimizing the weighted difference between flow vectors from neighbor points. To experiment, we drive a car on real roads and collected 7 sequences of data with a total distance over 40 kilometers. Our use sensor suite includes a RoboSense LiDAR, a Haskell 4D radar, a full HD RGB camera, and a sensing navigation system. We synchronize radar data to 10 Hz LiDAR point clouds and use pulse data for motion compensation. To evaluate different methods, we refer to the output from a 3D object detection module powered by the RoboSense LiDAR navigation system. We label the test data with human efforts for inspection and correction. The annotated test data can be used to evaluate models obtained from self-supervised learning. We compare our proposed rate flow with 7 baseline methods on the test set. As a result, rate flow achieves the best performance on all metrics. Qualitative results show rate flow can correctly estimate the flow vectors of both static and moving points. Here are some demos showing our qualitative results. The left is a video captured by our RGB camera, and the right shows the scene flow estimation results. We rub the blue point cloud 1 with the predicted scene flow to generate green points. Generally, the green points should be close to the magenta points if the scene flow is accurately predicted. So, as shown in our demos, our method is robust to different scenarios. We also evaluate our model on motion segmentation tasks, as shown in the figure. We also did ablation studies. And finally, thank you for watching the video.